Chapter 8. Engineering and Transportation. The field of service of a civil engineer has thus been eloquently stated by a recent writer in Chambers's journal. His duties call upon him to devise the means for surmounting obstacles of the most formidable kind. He has to work in the water, over the water, and under the water, to cause streams to flow, to check them from overflowing, to raise water to a great height, to build docks and walls that will bear the dashing of waves, to convert dry land into harbors, and low water shores into dry land, to construct lighthouses on lonely rocks, to build lofty aqueducts for the conveyance of water, and viaducts, for the conveyance of railway trains, to burrow into the bowels of the earth with tunnels, shafts, pits and mines. To span torrents and ravines with bridges, to construct chimneys that rival the loftiest spires and pyramids in height, to climb mountains with roads and railways, to sink wells to vast depths in search of water. By untiring patience, skill, energy and invention, he produces in these several ways works which certainly rank among the marvels of human power. The pyramids of Egypt, the roads, bridges and aqueducts built by the Chinese and by Rome, the great bridges of the Middle Ages, and especially those built by that strange fraternal order known as the Brothers of the Bridge, the ocean-defying lighthouses of a later period, these, and more than these, attest the fact that there were great engineers before the 19th century. But the engineering of today is the handmaid of all the sciences, and as they each have advanced during the century beyond all that was imagined, or dreamed of as possible in former times, so have the labors of engineering correspondingly multiplied. No longer are such labors classified and grouped in one field, called civil engineering, but they have been necessarily divided into great additional new and independent fields, known as steam engineering, mining engineering, hydraulic engineering, electrical engineering, and marine engineering. Within each of these fields are assembled innumerable appliances which are the offspring of the inventive genius of the century just closed. We have seen how one discovery, or the development of a certain art, brings in its train and often necessitates other inventions and discoveries. The development and dedication of the steam engine to the transportation of goods and men called for improvements in the roads and rails on which the engine and its load were to travel, and this demand brought forth those modern railway bridges which are the finest examples in the art of bridge making that the world has ever seen. The greatest bridges of former ages were built of stone and solid masonry. Now iron and steel have been substituted, and these light but substantial frameworks span wide rivers and deep ravines with almost the same speed and gracefulness that the spider spins his silken web from limb to limb. These, too, waited for their construction on that next turn in the wheel of evolution, which brought better processes in the making of iron and steel, and better tools and appliances for working metals, and in handling vast and heavy bodies. The first arched iron bridge was over the Severn at Coalbrookdale, England, erected by Abraham Darby in 1777. In 1793 one was erected by Telford at Buildwas, and in the same year Burton completed an arch across the Wear at Sunderland. The most prominent classes of bridges in which the highest inventive and constructive genius of the engineers of the century are illustrated are known as the suspension, the tubular and the tubular arch, the truss and cantilever. Suspension bridges consisting of twisted vines, of iron chains or of bamboo, or cane, or of ropes, have been known in different parts of the world from time immemorial, but they bear only a primitive and suggestive resemblance to the great iron cable bridges of the 19th century. The first notable structure of this kind was constructed by Sir Samuel Brown, across the Tweed at Berwick, England, in 1819. Brown was born in London in 1776 and died in 1852. He entered the Navy at the age of 18, was made commander in 1811, and retired as captain in 1842. We have alluded to the spider's web, and Smiles in his Self-Help, relates as an example of intelligent observation that while Captain Brown was occupied in studying the character of bridges with the view of constructing one of a cheap description to be thrown across the Tweed, near which he lived, he was walking in his garden one dewy autumn morning when he saw a tiny spider's web suspended across his path. The idea immediately occurred to him, of a bridge of iron wires. In 1829 Brown also was the engineer for suspension bridges built over the Esk at Montrose and over the Thames at Hammersmith. Before that time, a span in a bridge of 100 feet was considered remarkably long. Suspension bridges are best adapted for long spans, and have been constructed with spans more than twice as long as any other form. Sir Samuel Brown's bridge had a span of 449 feet. This class of bridges is usually constructed with chains or cables passing over towers, with the roadway suspended beneath. The ends of the chains or cables are securely anchored. The cables are then passed over towers, on which they are supported in movable saddles, so that the towers are not overthrown by the strain on the cables. Nice calculations have to be made as to the tension to be placed on the cables, the allowance for deflection, and the equal distribution of weight. The floorway in the earlier bridges of this type was supported by means of a series of equidistant vertical rods, and was lacking stiffness, but this was remedied by trussing the roadbed, using inclined stays extending from the towers and partially supporting the roadway for some distance out from the tower. The next finest suspension bridge was constructed by Thomas Telford and finished in 1826, across the Menai Strait to connect the island of Anglesey with the mainland of Wales. Telford was born in Dumfriesshire, Scotland, in 1757, and died in Westminster in 1834. Beginning life as a stonemason, he rose by his own industry to be a master among architects and a prince among builders of iron bridges, aqueducts, canals, tunnels, harbours and docks. The Menai Bridge was composed of chains or wire ropes, each nearly a third of a mile in length, and which descended 60 feet into sloping pits or drifts, where they were screwed to cast iron frames embedded in the rocks. The span of the suspended central arch was 560 feet, and the platform was 100 feet above high water. 7 stone arches of 52.5 feet span make up the rest of the bridge. But a suspension bridge was completed in 1834 by M. Chally of Lyon over the Sarn at Fribourg, Switzerland, which greatly surpassed the Menai Bridge. The span is 880 feet from pier to pier, and the roadway is 167 feet above the river. It is supported by 4 iron wire cables, each consisting of 1,056 wires. It was tested by placing 15 pieces of artillery, drawn by 50 horses and accompanied by 300 men crowded together as closely as possible, first at the center, and then at each extreme, causing a depression of 39.5 inches, but no sensible oscillation was experienced. Isambard Cade Brunel was another great engineer, who constructed a suspension bridge at the Isle of Bourbon in 1823, and the Charing Cross over the Thames at Hungerford in 1845, which was a footbridge, having a span of 675 feet, the longest span of any bridge in England. Then followed finer and larger suspension bridges in other parts of the world. It was across the Niagara in front of the Great Falls that in 1855 British America and the United States were joined by a magnificent suspension bridge, one of the finest in the world, and the 2 English-speaking countries were then physically and commercially united. At the opening of the bridge, one portion of which was for a railway, the shriek of the locomotive and the roar of the train mingled with the roar of the wild torrent 250 feet below. The bridge, 800 feet long, is a single span, supported by 4 enormous cables of wire stretching from the Canadian cliff to the opposite United States cliff. The cables pass over the tops of lofty stone towers arising from these cliffs, and each cable consists of no less than 4,000 distinct wires. The roadway hangs from these cables, suspended by 624 vertical rods. The engineer of this bridge was John A. Roebling, a native of Prussia, born there in 1806, and who died in New York in 1869. He was educated at the Polytechnic School in Berlin, and emigrated to America at the age of 25. His labors were first as a canal and railway engineer, then he became the inventor and manufacturer of a new form of wire rope, and then turned his attention to the construction of aqueducts and suspension bridges. After the Niagara Bridge, above described, he commenced another bridge of greater dimensions over the same river, which was finished within 2 or 3 years. His next work was the splendid suspension bridge at Cincinnati, Ohio, which has a clear span of 1,057 feet. In 1869, in connection with his son, Washington A. Roebling, he commenced that magnificent suspension bridge to unite the great cities of New York and Brooklyn, and which, by its completion, resulted in the consolidation of those cities as Greater New York. The Roeblings, father and son, were to the engineering of America what George Stephenson and his son Robert were to the locomotive and railway and bridge engineering of Great Britain. The Brooklyn Bridge, known also as the East River Bridge, was formally opened to the public on the 24th of May 1883. Most enormous and unexpected technical difficulties were met and overcome in its construction. Its total length is nearly 6,000 feet. The length of the suspended structure from anchorage to anchorage is 3,454 feet. A statement of the general features of this bridge indicates the nature of the construction of such bridges as a class, and distinguishes them from the comparatively simple forms of past ages. This structure is supported by two enormous towers, having a height of 276 feet above the surface of the water, carrying at their tops the saddles which support the cables, and having a span between them of 1,595 feet. The towers are each pierced by two archways, 31.5 feet wide, and 120.5 feet high, through which openings passes the floor of the bridge at the height of 118 feet above high water mark. There are four supporting cables, each 16 inches in diameter, and each composed of about 5,000 single wires. The wire is 1/8 size, 278 single wires are grouped into a rope, and 19 ropes bunched, to form a cable. The iron saddles at the top of the lofty towers, and on which the cables rest, are made movable to permit its expansion and compression, and they glide through minute distances on iron rollers in saddle plates embedded and anchored in the towers, in response to strains and changes of temperature. The enormous cables pass from the towers shoreward to their anchorages 930 feet away, and which are solid masses of masonry, each 132 by 119 feet at base and top, 89 feet high, and weighing 60,000 tons. The bridge is divided into 5 avenues, one central one for foot passengers, 2 outer ones for vehicles, and the others for the street cars. The cost of the bridge was nearly $15 million. 20 fatal and many disabling accidents occurred during the construction of the bridge. The great engineer Roebling was the first victim to an accident. He had his foot crushed while laying the foundation of one of the stone piers, and died of lockjaw. It was necessary to build up the great piers by the aid of caissons, which are watertight casings built of timber and metal and sunk to the river bed and sometimes far below it, within which are built the foundations of piers or towers, and into which air is pumped for the workmen. A fire in one of the caissons, which necessitated its flooding by water, and to which the son, Washington Roebling, was exposed, resulted in prostrating him with a peculiar form of caisson disease, which destroyed the nerves of motion without impairing his intellectual faculties. But, although disabled from active work, Mr. Roebling continued to superintend the vast project through the constant mediation of his wife. Tubular bridges. These are bridges formed by a great tube or hollow beam through the center of which a roadway or railway passes. The name would indicate that the bridge was cylindrical in form, and this was the first idea. But it was concluded after experiment that a rectangular form was the best, as it is more rigid than either a cylindrical or elliptical tube. The adoption of this form was due to Fairbairn, the celebrated English inventor and engineer of iron structures. The Menai Tubular Railway Bridge, adjacent to the suspension bridge of Telford across the same strait, and already described, was the first example of this type of bridge. Robert Stephenson was the engineer of this great structure, aided by the suggestions of Fairbairn, and other eminent engineers. This bridge was opened for railway traffic in March, 1850. It was built on 3 towers and shore abutments. The width of the strait is divided by these towers into 4 spans, 2 of 460 feet each, and two of 230 feet. In appearance, the bridge looked like one huge, long, narrow iron box, but it consisted really of 4 bridges, each made of a pair of rectangular tubes, and through one set of tubes the trains passed in going in one direction, and through the other set in going the opposite direction. These ponderous tubes were composed of wrought iron plates, from 3/8 to 3/4 of an inch thick, the largest 12 feet in length, riveted together and stiffened by angle irons. They varied in height, the central ones being the highest, and those nearest the shore the lowest. The central ones are 30 feet high, and the inner ones about 22 feet. Their width was about 14 feet. They were built upon platforms on the Carnarvon shore, and the great problem was how to lift them and put them in place, especially the central ones, which were 460 feet in length. Each tube weighed 1,800 pounds, and they were to be raised 192 feet. This operation has been described as the grandest lift ever effected in engineering. It was accomplished by means of powerful hydraulic presses. Another and still grander example of this style of bridge is the Victoria at Montreal, Canada. This also was designed by Robert Stephenson and built under his direction by James Hodges of Montreal. Work was commenced in 1854 and it was completed in December 1859, and opened for travel in 1860. It consists of 24 piers, 242 feet apart, except the center one, from which the span is 330 feet. The tube is in sections and quadrangular in form. Every plate and piece of iron was made and punched in England and brought across the Atlantic. In Canada little remained to be done but to put the parts together and in position. This, however, was in itself a Herculean task. The enormous structure was to be placed 60 feet above the swift current of the broad St. Lawrence, and wherein huge masses of ice, each block from 3 to 5 feet in thickness, accumulated every winter. The work was accomplished by the erection of a vast rigid stage of timber, on which the tubes were built up plate by plate. When all was completed the great staging was removed, and the mighty tube rested alone and secure upon its massive wedge-faced piers rising from the bedrock of the flood below. The tubular arch bridge. This differs from the tubular bridge proper, in that the former consists of a bridge the body of which is supported by a tubular archway of iron and steel, whereas in the latter the body of the bridge itself is a tube. The tubular arch is also properly classed as a girder bridge because the great tube which covers the span is simply an immense beam or girder, which supports the superstructure on which the floor of the bridge is laid. A fine illustration of this style of bridge is seen in what is known as the Aqueduct Bridge over Rock Creek at Washington, D.C., in which the arch consists of 2 cast iron jointed pipes, supporting a double carriage and a double streetcar way, and through which pipes all the water for the supply of the city of Washington passes. General M.C. Meigs was the engineer. Another far grander illustration of such a structure, in combination with the truss system, is that of the Illinois and St. Louis Bridge, across the Mississippi, of which Captain James B. Eads was the engineer. There are 3 great spans, the central one of which has a length of about 520 feet, and the others a few feet less. 4 arches form each span, each arch consisting of an upper and lower curved member or rib, extending from pier to pier, and each member composed of 2 parallel steel tubes. Truss and truss-arched bridges. These, for the most part, are those quite modern forms of iron or wooden bridges in which a supplementary framework, consisting of iron rods placed obliquely, vertically or diagonally, and cemented together, and with the main horizontal beams either above or below the same, to produce a stiff and rigid structure, calculated to resist strain from all directions. Previous to the 19th century, the greatest bridges being constructed mostly of solid masonry piers and arches, no demand for a bridge of this kind existed, but after the use of wrought iron and steel became extensive in bridge making, and as these apparently light and airy frames may be extended, piece by piece across the widest rivers, straits, and arms of the sea, a substitute for the great, expensive, and frequent supporting piers became a want, and was supplied by the system of trusses and truss arches. The truss system has also been applied to the construction of vast modern bridges in places where timber is accessible and cheap. Each different system invented bears the name of its inventor. Thus, we have the Ryder, the Fink, the Bolman, the Whipple, the Howe, the Jones, the Linville, the McCallum, Townes lattice and other systems. What is called the cantilever system has of late years to a great extent superseded the suspension construction. This consists of beams or girders extending out from the opposite piers at an upward diagonal angle, and meeting at the center over the span, and they're solidly connected together, or to horizontal girders, in such manner that the compression load is thrown onto the supporting piers, upward strains received at the center, and side deflections provided against. It is supposed that greater rigidity is obtained by this means than by the suspension, and, like the suspension, great widths may be spanned without an under-supporting framework. Two fine examples of this type are found, one in a bridge across the Niagara adjacent to the suspension bridge above described and one across the River Forth at Queen's Ferry in Scotland. The Niagara Bridge is a combination of cast steel and iron. It was designed by C.C. Schneider and Edmund Hayes. It was built for a double-track railroad. The total length of the bridge is 910 feet between the centers of the anchorage piers. The cantilevers rest on two gigantic steel towers, standing on massive stone piers 39 feet high. The clear span between the towers is 470 feet, and the height of the bridge, from the mad rush of waters to the car track, is 239 feet. Messrs. Fowler and Baker were the engineers of the Forth Railway Bridge. It was begun in 1883 and finished in 1890. It is built nearly all of steel, and is one of the most stupendous works of the kind. It crosses two channels formed by the island of Inchgarvie, and each of the channel spans is 1,710 feet in the clear and a clear headway of 150 feet under the bridge. 3 balanced cantilevers are employed, poised on 4 gigantic steel tube legs supported on 4 huge masonry piers. The height of the bridge above the piers is 330 feet. The cantilever portion has the appearance of a vast elongated diamond. Steel lattice work of girders forms the upper side of the cantilever, while the underside consists of a hollow curve approaching in form a quadrant of a circle drawn from the base of the legs or struts to the ends of the cantilever. Such is the growth of these great bridges with their tremendous spans across which man is spinning his iron webs, that when seen at night with a fiery engine pulling its thundering train across in the darkness, one is reminded of Milton's description, over the dark abyss whose boiling gulf tamely endured a bridge of wondrous length, from hell continued, reaching the utmost orb of this frail world. The lighthouses of the century, in masonry, do not greatly excel in general principles those of preceding ones, as at Eddystone, designed by Smeaton. Nicholas Douglas, however, invented a new system of dovetailing, and great improvements have been made in the system of illuminating. Lighthouses are also distinguished from those of preceding centuries by the substitution of iron and cast steel for masonry. The first cast iron lighthouse was put up at Point Morant, Jamaica, in 1842. Since then they have taken the form of iron skeleton towers. One of the latest and most picturesque of lighthouses is that of Bartholdi's Statue of Liberty enlightening the world, the gift of the French government to the United States, framed by M. Eiffel, the great French engineer, and set up by the United States at Bedloes Island in New York Harbor. It consists of copper plates on a network of iron. Although the statue is larger than any in the world of such composite construction, its success as a lighthouse is not as notable as many farther seaward. In excavating, dredging and draining, the inventions of the century have been very numerous, but, like numerous advances in the arts, such inventions, so far as great works are concerned, have developed from and are closely related to steam engineering. The making of roads, railroads, canals and tunnels has called forth thousands of ingenious mechanisms for their accomplishment. A half-dozen men with a steam power excavator or dredger can in one day perform a greater extent of work than could 1,000 men and 1,000 horses in a single day a few generations ago. An excavating machine consisting of steel knives to cut the earth, iron scoops, buckets and dippers to scoop it up, endless chains or cranes to lift them, actuated by steam, and operated by a single engineer, will excavate cubic yards of earth by the minute and at a cost of but a few dollars a day. Dredging machines of a great variety have been constructed. Drags and scoops for elevating, and buckets, scrapers and shovels, and rotating knives to first loosen the earth, suction pumps and pipes, which will suck great quantities of the loosened earth through pipes to places to be filled. These and kindred devices are now constantly employed to dig and excavate, to deepen and widen rivers, to drain lands, to dig canals, to make harbors, to fill up the waste places and to make courses for water in desert lands. Inventions for the excavating of clay, piling and burning it in a crude state for ballast for railways, are important, especially for those railways which traverse areas where clay is plentiful, and stones and gravel are lacking. Sinking shafts through quicksands by artificially freezing the sand, so as to form a firm frozen wall immediately around the area where the shaft is to be sunk, is a recent new idea. Modern countries especially are waking up to the necessity of good roads, not only as a necessary means of transportation, but as a prerequisite to decent civilization in all respects. And, therefore, great activity has been had in the last third of a century in invention of machines for finishing and repairing roads. In the matter of sewer construction, regarded now so necessary in all civilized cities and thickly settled communities as one of the means of proper sanitation, great improvements have been made in deep sewerage, in which the work is largely performed below the surface and with little obstruction to street traffic. In connection with excavating and dredging machines, mention should be made of those great works in the construction of which they bore such important parts, as drainage and land reclamation, such as is seen in the modern extensions of land reclamation in Holland, in the Haarlem Lake District in the north part of England, the swamps of Florida, and the drainage of the London District, in modern tunnels such as the Hoosac in America, and the three great ones through the Alps, the Mont Cenis, St. Gothard, and Arlberg, the work in which developed an entirely new system of engineering, by the application of newly discovered explosives for blasting, new rock drilling machinery, new air compressing machines for driving the drill machines and ventilating the works, and new hydraulic and pumping machinery for sinking shafts and pumping out the water. The great canals, especially the Suez, developed a new system of canal engineering. Thus by modern inventions of devices for digging and blasting, dredging and draining and attendant operations, some of the greatest works of man on earth have been produced, and evinced the exercise of his highest inventive genius. If one wishes an ocular demonstration of the wonders wrought in the 19th century in the several domains of engineering, let him take a Pullman train across the continent from New York to San Francisco. The distance is 3,000 miles and the time is 4 days and 4 nights. The car in which the passenger finds himself is a marvel of woodwork and upholstery, a description of the machinery and processes, for producing which belongs to other arts. The railroad tracks upon which the vehicle moves are in themselves the results of many inventions. There is the width of the track, and it was only after a long and expensive contest that countries and corporations settled upon a uniform gauge. The common gauge of the leading countries and roads is now 4 feet 8.5 inches. A greater width is known as a broad gauge, a less width as a narrow gauge. Then as to the rail, first the wooden, then the iron and now the steel, and all of many shapes and weights. The T-rail invented by Birkensaw in 1820, having 2 flanges at the top to form a wide berth for the wheels of the rolling stock, the vertical portion gripped by chairs which are spiked to the ties, is the best known. Then the frogs, a V-shaped device by which the wheels are guided from one line of rails to another, when they form angles with each other, the car wheel made with a flange or flanges to fit the rail, and the railway gates, ingenious contrivances that guard railway crossings and are operated automatically by the passing trains, but more commonly by watchmen. The car may be lighted with electricity, and as the train dashes along at the rate of 30 to 80 miles an hour, it may be stopped in less than a minute by the touch of the engineer on an air brake. Is it midwinter and are mountains of snow encountered? They disappear before the railway snow plow more quickly than they came. It passes over bridges, through tunnels, across viaducts, around the edges of mountain peaks, every mile revealing the wondrous work of man's inventive genius for encompassing the earth with speed, safety and comfort. Over 500,000 miles of these railway tracks are on the Earth's surface today. Not only has the railway superseded horsepower in the matter of transportation to a vast extent, but other modes of transportation are taking the place of that useful animal. The old-fashioned stagecoach, and then the omnibus, were successively succeeded by the streetcar drawn by horses, and then about 20 years ago the horse began to be withdrawn from that work and the cable substituted. Cable transportation developed from the art of making iron wire and steel wire ropes or cables. And endless cables placed underground, conveyed over rollers and supported on suitable yokes, and driven from a great central powerhouse, came into use, and to which the cars were connected by ingeniously contrived lever grips, operated by the driver on the car. These great cable constructions, expensive as they were found more economical than horse power. In fact, there is no modernly discovered practical motive power but what has been found less expensive both as to time and money than horsepower. But the cable for this purpose is now in turn everywhere yielding to electricity, the great motor next to steam. The overhead cable system for the transportation of materials of various descriptions in carriers, also run by a central motor, is still very extensively used. The cable plan has also been tried with some success in the propelling of canal boats. Canals themselves, although finding a most serious and in some localities an entirely destructive rival in the railroad, have grown in size and importance, and in appliances that have been substituted for the old-style locks. The latest form of this device is what is known as the pneumatic balance lock system. It has been said by Octave Chanute that progress in civilization may fairly be said to be dependent upon the facilities for men to get about, upon their intercourse with other men and nations, not only in order to supply their mutual needs cheaply, but to learn from each other their wants, their discoveries and their inventions. Next to the power and means for moving people, come the immense and wonderful inventions for lifting and loading, such as cranes and derricks, means for coaling ships and steamers, for handling and storing the great agricultural products, grain and hay, and that modern wonder, the grain elevator, that dots the coasts of rivers, lakes and seas, receives the vast stores of golden grain from thousands of steam cars that come to it laden from distant plains and discharges it swiftly in mountain loads into vessels and steamers to be carried to the multitudes across the seas, and to satisfy that ever-continuing cry, "Give us this day our daily bread."